Hello and welcome to Xamarin University. My name is Adrian Stevens, and I'll be your instructor today for this recording of Enterprise 170, Securing Local Data. Before we get started, please make sure you've downloaded the course materials. If you haven't done so already, head on over to university.xamarin.com and download the package for Enterprise 170. Now, there are two big themes in this course: how to store secrets locally, and how to perform some common cryptographic operations. Now, cryptography is a large, complex subject, so we also need to discuss a few topics on, big picture issues like deciding what kinds of data need protecting and how to choose a crypto API. We'll do things in a cross-platform way, so all the code we write will be usable from a portable class library project, and this includes our Xamarin Forms applications. And before we talk about how to perform cryptography, we need to discuss whether it's worth the time and effort to do it at all. News stories about data breaches regularly appear in the mainstream press, and this means most people have some level of awareness of computer security and data privacy. And users will likely be aware that they're placing their trust in you when they give your app their confidential information. And it can be really damaging to your brand and credibility if users discover your app has not properly secured their data. Apps collect a lot of information from their users, and some of it will be considered personal or sensitive in nature. Now, one of the most discussed categories is financial information, so things like credit card numbers and banking details. But keep in mind that passwords and OAuth tokens to access financial services can be just as important as direct financial details, since they can be used, of course, to access a user's accounts. Another category is meta information about the user, so their name, government ID numbers, addresses, etc. These ID numbers are often used to establish identity, so keeping them private is very important to most users. And these users may not want their addresses to be widely disseminated to avoid unwanted mail or attention. Many users also consider their physical statistics to be confidential. So, for example, some people want to avoid sharing their medical history or their weight with their employer and coworkers. And finally, anything that documents personal activities, like photos, even calendar appointments, can also be considered sensitive. And an example of that, users may not want to reveal what they do in their free time to their employer. The easiest way to avoid problems with disclosing user data is to avoid collecting it in the first place. If you don't have it, you can't reveal it. Generally, you should collect the minimum amount of information you need for your app to function. And you should also consider establishing a collection policy, and this will let your users know what data you collect and why you're collecting it. There's a trade-off between convenience and security. So storing user data is convenient for the user, since they don't need to re-enter details every time they run your application. However, each piece of information that you retain increases your responsibility and the consequences of a data breach. So you may want to consider asking the user to re-enter data as needed rather than storing it persistently. Now, if you are going to store data, you should secure any sensitive data that you retain. Sensitive data generally means information that could cause financial or physical harm if made public. And securing data typically means using encryption. There is a cost to doing encryption, so you need to balance security against code complexity and performance, especially on low-power mobile devices. Now, some governments impose legal requirements for handling data. This most often applies to financial and medical information. However, you should check the requirements for your sales area to verify if there are any laws that may apply to your application. Let's test our knowledge with a flash quiz. I highly encourage you to pause the video after I ask the questions. Think about it before revealing the answer. So my first question to you: in what ways could disclosing users' medical records be damaging? Now here are just some possible answers, and of course there could easily be more. Think about insurance rates. Leaking medical history or personal physical conditions could have effect on insurance rates. This might be an extreme case, but possibly loss of employment. We hope our employers are not going to be prejudiced against medical conditions, but that type of personal information should be stored securely and remain private. Probably a more obvious one is personal embarrassment. We don't always want to leak our personal statistics, our history, our medical conditions. And worst case could even be legal repercussions depending on, really your employment or what is done with that data. Look at another question. You should encrypt all information related to the user that you capture and store. Is this true or is this false? And this is, of course, not a simple question, but the general answer is false. Now, it might not be unreasonable to answer true here, and you're going to have to balance out what you think is sensitive or personal information. But remember that encryption does have a cost, and it's going to make your code more complex and potentially slower. So it might be more precise to say that you should encrypt any personal sensitive information rather than all user data. So consider a game where you capture the user's score. This is certainly related to that user, but it's unlikely to be personal or sensitive since it's likely to be shared automatically to the game's leaderboard and doesn't need to be encrypted when stored. Now, once you realize that your app will collect and store personal or sensitive data, you'll want to store it securely, as we've discussed. In this class, we'll use Xamarin Auth to store secrets on device in a cross-platform way. In this next section, we're going to explore Xamarin Auth, and we'll use it to store, retrieve, and delete a user's personal information on devices. So once you've decided to retain users' personal or sensitive data, make sure to store it securely. So typically this means encrypting the data so it will be difficult for an attacker to recover even if they get possession of the device and their data files. Now, most platforms have their own APIs to encrypt data and then store the encrypted data on that device. This is true for iOS, Android, and Windows. On iOS, you can use the keychain. On Android, there's the key store, and Windows has the password vault. And each of these handles both encryption and storage for you. Now, if you're writing a cross-platform application, using the native APIs can be inconvenient since it requires writing the same code multiple times in multiple ways, of course using those different APIs on each platform and then having some way to abstract it and use it in a common pattern. Each API has many details you'll need to learn as well. As an example, Password Vault on Windows Phone limits you to only 10 entries, and this is going to require you to structure your data in a way that's going to fit within those 10 entries. So what exactly is Xamarin Auth? Well, it's a software package that helps you store sensitive user data on the device. It is written and maintained by Xamarin, and it's designed to be cross-platform. It supports iOS, Android, Windows Phone, and the new Universal Windows platform, which will include Windows 10. And it's available from the Xamarin Component Store or as a NuGet package. Also worth noting, Xamarin Auth also helps you do OAuth, which means it allows you to securely connect to OAuth protected services. We won't be covering this in this class, but there is a follow-up course specific to OAuth. Now, Xamarin Auth gives you a clean, platform-independent API, but behind the scenes, it uses each platform's native APIs to store your data. So your code stays simple with very few platform dependencies. So on iOS, Xamarin Auth uses the keychain APIs to store your data. Keychain will encrypt the data and store it securely both on the device and optionally have it backed up to iCloud. On Android, Xamarin Auth uses a key store. The Android key store APIs do not include persistent storage, so Xamarin Auth creates a private file to store the key store data. The data is encrypted by the key store and it's saved in that file. Now, on Windows Phone, Xamarin Auth encrypts the data and then stores it in files located in the isolated storage for your application. Xamarin Auth's unit of storage is an account. And the account object represents a collection of data associated with a particular user. Now we can see the properties on screen. The username is intended to store the login name or display name of the user, but it's up to you as a developer to decide what value to place here, and it's not necessarily user-facing, so you can use any value that makes sense in your code. There's also a properties dictionary, and this is where you'll store your data, and you can put anything reasonable you like in here. And finally, there's the cookies property. So the account object was designed to work with social networks, so it has a cookie container property. And if you're not working with a social network, it's very likely that you'll leave this empty. Now, creating the account is just standard C#. You're going to allocate the object and load values into its properties. Most of your data will likely go into the properties dictionary. And it can store passwords, encryption keys, OAuth tokens. But note the dictionary stores strings, so you will need to convert things like encryption keys from byte arrays to string for storage. And we also have an account store. And the account store class is responsible for storing account objects on the device. And it provides a fairly standard set of operations for data storage, so it can find and save and delete objects. Now you see service ID used here on the slide, and we're going to talk about that in just a moment. But for now, notice how all of the operations work with account objects. So a typical pattern might be to create and save an account object when you first get some user data, and the account is then stored persistently on device. The user can close the app and the data will be saved, and when the user returns to the app, you'll use the find method to retrieve their data from disk. And of course, if you're finished with the data, you can delete the entire account from the store. Account store requires you to pass a string called the service ID, which we saw on the previous slide. And this is required for every operation. So for find, save, and delete. Now remember that Xamarin Auth is set up to work with social network accounts. So in that context, the service ID is fairly intuitive. Suppose you have a user that has accounts with many different social networks, so Facebook, Google, LinkedIn, etc. You would likely have separate account objects for each network. So for the account containing their Facebook data, you could choose a service ID of Facebook. Now the choice of the string is totally up to you, it's arbitrary, and it's common to make it something that intuitively matches the source of the data. But if you're only using a single account, you can use any ID you like. Now, service ID lets you avoid having to make the username unique across all accounts. So for example, suppose you have a user named Bob, you can create several account objects all with that same username, again across maybe different social networks. And when you store those accounts in the account store, you'll have different service IDs to uniquely identify them. And here we see the account store class again. And just notice that each operation takes a string service ID argument. So if you think of account store as similar to a database that stores account objects, then the combination of username and service ID serves as really the primary key for each account. Remember that the username by itself isn't enough to uniquely identify an account. We used the example earlier of a user named Bob that has accounts on both Facebook and Google+, with Bob as the username on both. So for example, when you delete an account from Account Store, the account to be deleted will be uniquely identified using the combination of username and service ID. To create an account store, we use a factory creation pattern. We use the account store create method to create an instance, and once you have the store instance, you can start calling the find, save, and delete methods. On iOS and Windows Phone, the account store create method doesn't take any parameters. On Android, however, the creation pattern for account store is just a little bit different. You need to pass a context to the create method, and the context is used to create or open that file that will store the serialized accounts. So once you have an account store, the code to store an account is the same for all platforms. You first create the account object, load it with the user data, and then call the save method on the account store, passing in your account instance. An account store provides a way to get all of the accounts for a given service ID. The find accounts for service method takes that service ID as a string and then returns an IEnumerable collection of accounts with all the accounts for that service. The username is not considered in this lookup. So you'll need to do filtering yourself if you're looking up a specific account. So you'll get all of the accounts for the service ID, then search through the results looking for the username you're searching for. And you could of course use a link expression here instead. Use the account store's delete method to remove an account. You pass in an account object that's used to get the username. You also give the service ID, and then Xamarin Auth ensures that both the service ID and username match before deleting the entry. Alright, let's see Xamarin Auth in an actual solution. So here I've opened up a Xamarin Form solution with some existing code. It already has some UI defined and just a little bit of logic. We've got head projects or platform-specific projects for both Android and iOS, and the shared code is a shared project. We'll take a closer look in just a moment, but the first thing I'm going to do is add Xamarin Auth to both platform-specific projects. And I'm going to do this using the Xamarin component store. And it's as simple as searching for xamarin.auth. And Xamarin Auth is also available via NuGet, and either one is fine. Let's add this for iOS as well. And we're all set. Before we start coding, I want to show you the application in its current state. And as you can probably guess, this is a diary application. This is probably a good candidate for something where you might want just a little bit of extra security, a little bit of validation to make sure no one's peering in at your private diary entries. We see our initial screen is a login screen. We can log in the diary, it takes a username and password, but currently it accepts any parameters for the username and password, and it will let us in. This screen here is designed to show existing diary entries. See, we don't have any currently, but we can add new ones via the plus button. Add some text, click the save button, and ideally this will save new diary entries. That logic's not completed yet. So currently we have a functional UI, but no logic to actually validate the user or save our diary entries. We're going to fill in some of these blanks. In my shared project, I have an account manager class. This is a nice central class to handle the account stores, and the basic login validation. And it already has a number of methods stubbed out, and these are already wired up to the UI. So when we click in our login button, it tries to log into the account. When we click the create new account button, it calls our create and save account method, and the like. And we're going to fill these in. I'm going to start at the bottom with the get account from store method. Now notice this accepts an account store and a username. Now this might feel a little bit out of order, but I'll show you this actually is going to come together quite nicely. So we want to get an account from the account store based on the username. We've got a little bit of validation here already, just making sure our parameters aren't null. We've already got an account store. So let's get the account objects out of the account store. We do this using the store's find account. I went find accounts for service method. And this takes a service ID. You might remember the service ID, well, it represents the service that we're storing in our account store. And you might have multiple service IDs if you're dealing with multiple, say, social networks, for example. Now in our case, our service is early. It's our diary service, if you like. We only have one service ID we're going to need. So we've got a constant string defined up top called service ID conveniently, and it's just the text diary. The text can be anything as long as you use it consistently. And we use our constant string here just to avoid typos, those inline string literals. So we're going to find all the accounts based off the service ID. Now we haven't done this yet, but I'm only going to store one account per username. So I don't need all of the accounts for a given username, and in fact I know there only will be one. But you see this returns an IE enumerable, returns a collection of account objects. So let's get the first one out. Now there's lots of ways of doing this, but in this case I'll use just a little bit of link. So from that accounts collection, and call first or default, and just a touch of link here. And remember, our account objects have a username property, and that's just a string. So we'll just check that against our passed in username. If they're a match, we're all set. And there we are, just that easy. Return the first account for our service ID and our username. Off to a great start, but of course we haven't saved any data yet, so I want to do that next. So these top two methods are wired into our UI. And our first one is to create a new account, and we'll create and of course save that account. Now the first thing we're going to need is the account store. Our last method had it passed in, that's because we're going to call it, but we need to get the account store from somewhere. Now remember, the account store is created via a create factory method, and this is because we actually get the correct account store instance. There's only one. So we use that factory method to get our reference. Now, the create method is a little bit different depending on the platform. So we've got create for Android that takes a context, and iOS doesn't have any input parameters. So we've got a convenience method called getAccountStore, and that just calls the correct version of accountStore.create depending on the platform, and that means we don't have to think about the platform. So we're going to use this version here, getAccountStore. So we'll do that first. getAccountStore. And then we're going to use our getAccountFromStore method that accepts that account store and a username. And the username is coming in from the UI in that username entry field. Let's just pass that in. Now, we only want to save an account if we don't already have an existing user under that name. So I want this to be null. I don't want to get a return from getAccountFromStore right now. So if it's not null, I'm going to return false. That means we can't create a new account. So at this point, if we've gotten past that return false, we know we don't have a matching user. Let's create one. So we'll make a new account, and we just instantiate our account object, and we'll use the overload that takes the username, and that's just going to set that username property in our account object. We also want to store the password in our account. Now, full disclosure, this is not the ideal way to manage passwords, and I'll show you another way later on. This will do for now though, for some basic validation. Now our account object has a properties property. This is a dictionary, it is a property, and it's called properties. And it's a dictionary that uses string keys and stores string values. And so we're just going to store our password in our account. For convenience and just for a little bit of safety, I've got another const string we'll use for the key, PW key, and we're just going to store our passed in password. Perfect. We now have our password in our account. Let's make sure I got that spelled right. Properties, there we go. I think maybe the IntelliSense is, you know what? It's a dictionary, .add. Perfect, all set. Now we just need to save our account in the account store. We already have that, of course. And this is easy as calling store in its save method. It takes an account, and there's that service ID. This is how we set the service ID or associate it with our account. And of course, remember earlier on, we used the service ID to then retrieve the account. As long as these match, we are all set. Coming together nicely. But the last thing I want to do is that little bit of validation when you log in after you've created an account. Use the application once, create an account, and then log in again and validate your account. And we'll do this in the login to account method. Similar to before, we need a reference to our account store, and we'll just use our getAccountStore helper method. We also want to try and load the account. And again, we'll use getAccountFromStore, that first method we wired up. This takes the account store, and it also takes the username. Again, that's passed in from the UI. Now, This other Boolean method, and we want to return true if we have an account object and it has the password stored within it. So we can do a little bit of clever comparisons here. There's lots of ways of wiring this up, but I'll do this in one line. So if the account is not null, then we're happy. And we want to make sure the password is saved in here and it matches our password. So it's a dictionary, so I can reference the value directly via the key. Remember, it's PW key, and if that string value matches our passed-in password, we're all set. So if we have an account and the password matches, we return true, otherwise false. And there's a little bit of UI in place to make this all work. So now I'll run the application and we'll try it again. Here's our app. So let's try a username we haven't saved yet, which is really, well, heck, that's anything. I'm gonna hit login, and the login failed. You see that method has returned false. The account doesn't exist, our login has failed. So let's put something more meaningful to me. I'll just use my name, my secret password, and I'll create that new account. We've gone to the next screen, so it looks like it's worked. Now we haven't put in the logic yet to save our diary entries, but we have validated our username and password. So I'm going to stop the application. I'm going to run it again. I'll put in my username. Tried logging in. The login has failed. I did not put my password in. But if I put in the same password I used earlier, we now go on to the next screen. Off to a great start. In this section, we learned about Xamarin Auth, and we saw how to create and populate account objects and store them using the account store. Now, if you're writing an app for a single platform, you're likely going to use the crypto API supplied by that platform. But if your app is cross-platform, this decision gets a little bit more difficult. Do you write the crypto code once using a cross-platform API, or multiple times using each platform-specific API? Of course, here we prefer to do less work, and we'd like to find a cross-platform solution. So this section covers some considerations when deciding between platform-specific and cross-platform crypto APIs. We'll start by listing a sampling of available options. Then we'll do a pros and cons analysis of using a cross-platform solution versus the native APIs. And finally, we'll give some brief guidance on how to choose the right API for your solution. So suppose you're building a cross-platform app, perhaps using Xamarin Forms. You're going to have shared code in either a portable class library or a shared project. Then you'll have one or more platform-specific projects for each platform you're targeting. And you want to put as much code as you can into your shared code or your PCL instead of rewriting that code for each platform. And we actually have a wide selection of APIs to choose from for our crypto operations. So as mentioned, each platform has their own APIs, their own native implementations of various cryptographic algorithms. Mono also implements the types from the system security and system security cryptography namespaces. So all those great .NET APIs you might be used to from Windows are available in Xamarin iOS and Xamarin Android. There are, of course, third-party options. So third parties have added a uniform layer over some of those platform-specific and mono APIs, and these generally do not implement any cryptography on their own, but they let you access existing libraries in a cross-platform uniform way. And we're going to look at one of these called Pcl Crypto in our next section. But also keep in mind there are third-party libraries that do include their own crypto code, and you'll need to decide which approach to take in your applications. And each have benefits, and we'll look at a few points next that can help you choose. So if you plan to target low-power mobile devices, then efficiency of implementation may be a high priority for you. So some manufacturers do include hardware implementations of some crypto algorithms, which typically make them significantly faster to execute. Now, when comparing software implementations, there's not always a clear winner. Sometimes the native APIs are faster, sometimes the third-party code is faster. So if performance is a top priority, you'll probably need to do some testing and some research. Now, some developers prefer to use the APIs supplied by the platform, and that is, of course, a reasonable choice. So this means on iOS, you would use the iOS APIs, on Android, the Android APIs, etc., etc. And so you would end up writing your crypto code multiple times. Now, a reasonable argument for this approach is increased confidence. For example, as a developer, you might feel that the Android APIs would have the full resources of Google behind them, so they may be created by experts and ideally very thoroughly tested. Now, additionally, you may think that your users would also appreciate it if you tell them, hey, all of the crypto operations in this application are performed inside of Apple's secure enclave, for example. All right, relying on these big companies to implement that cryptographic code as well as they possibly can. Now, another consideration is that by using the platform-specific APIs, you're writing a lot of code, right? It is duplicate work. For supporting 3-4 platforms is a lot of work to do. And you are going to need to implement all of your operations on each supported platform. Now, this may not surprise you, but the platform-specific APIs are unique and in some cases quite different. If you learn how to do an operation on one platform, that knowledge may not help you all that much when you move to the next. So it is time-consuming to implement these same operations multiple times. As well, it can be error-prone, again with the differences of the APIs and just the fact that cryptography itself is complex, and it is fairly easy to make mistakes if you're not experienced, or let's be honest, if you're not an expert. So, of course, maybe you're coming from a .NET background, and a lot of you probably are. And so it's natural to ask at this point whether we can just use system security. There's a lot of APIs in that namespace, and those .NET APIs provide a quite comprehensive set of crypto APIs, and they are available in the mono implementation of the .NET base class libraries. And they might already be very familiar to you if you've been working with .NET. Now, unfortunately, only a very small subset of the system security classes are available within a portable class library. They are available on the individual platforms, but they are more difficult to use in a cross-platform way. And really what this means is it doesn't help you all that much when you're writing your crypto code. You still need to find some way to abstract it, and you're still implementing it per platform. So ultimately, the decision comes down to probably a lot of things like corporate policy, your developer preferences, and really your background and your experience. And there isn't necessarily a right solution, but we are going to give you a suggested solution in the next section. So hopefully we've given you some ideas of the types of considerations that you should be thinking about when implementing crypto, or more specifically, picking a crypto strategy for your cross-platform applications. So now I want to introduce something called Pco Crypto. And we're going to focus on one cross-platform solution. And this gives you a uniform interface over the mono and platform APIs. And as the name implies, it can be used from your PCL. It's right in the name, Pcl Crypto. And so you can write your crypto code once and share it across all of your target platforms. And really, as developers, that's usually what we're looking for. So we'll first talk about the goals and the organization of Pcl Crypto. It's important to understand the tools you're using before you're implementing them in your application, and this is especially true with cryptography. After that, we'll do a quick overview of the services it provides. Now, we won't write any code in this section, it's just an introduction to Pcl Crypto. So let's cut right to the chase. Pcl Crypto is a great option for developers looking to implement efficient cryptographic code, as it does call the native crypto APIs on each platform where appropriate. And it's also an excellent choice when developing cross-platform mobile crypto-enabled apps, as of course it's usable from within our PCLs as we discussed. So what exactly is Pcl Crypto? Well, it's an open source project, and it wraps the native and mono crypto APIs and exposes them via a uniform common API. Now, unlike system security, Pcl Crypto is fully usable within a PCL, as we discussed already. And of course, probably the next question you have is, what does it support? It supports iOS, Android, Windows Phone, and Windows applications. And that includes both mobile and desktop, including the new UWP APIs. Now, the interesting thing about Pcl Crypto is that it provides access to a variety of security algorithms. As I mentioned, some of them implemented by the platform-specific APIs, and some of them managed by the .NET or mono layers. And the specific API exposed by the library is determined based on whether it's implemented by the platform and how it performs. That's right, performance is a consideration for the Pcl Crypto author. Now, unfortunately, I don't have clear documentation on exactly what will be executed for each platform. However, the library is open source, so if you need to determine this, you can go look at the source code if you're interested. Pcl Crypto was designed to expose most common crypto functions, and as a result, we have a fairly complete set of crypto APIs using Pcl Crypto. This includes asymmetric encryption, so we have algorithms like RSA. It of course also supports symmetric encryption, such as AES. It can be used to generate cryptographic hashes. It can also message authentication codes. And it provides a number of helper functions like random number generation and the creation of cryptographically random data. And so for the purposes of securing local data, we'll be focusing on symmetric encryption and hashing, but keep in mind these other features are available in Pcl Crypto. Let's talk about the Pcl Crypto API. The API is modeled after the WinRT Crypto API, and this is familiar to a lot of Windows developers out there. It also has another benefit. It means that you can get some guidance on usage right from the MSDN documentation. However, Pcl Crypto is not a perfect match to the WinRT APIs. There were some concessions made, and this is both to ease development and also to aid in cross-platform use. For example, especially for those of you already familiar with the WinRT APIs, WinRT uses the iBuffer interface. Pcl Crypto is simplified and simply returns a byte array. So you're going to want to consult the Pcl Crypto documentation or source code first if you have any questions on a specific feature or function. Now, when working with Pcl Crypto, you're going to start with the WinRT Crypto class. And this is the main entry point to those crypto APIs. Notice this class includes APIs for many common crypto functions. So we see encryption, hashing, MAC generation. There's also a second class you'll use in Pcl Crypto, and it's called NetFX Crypto. And this is keeping in the spirit of exposing a familiar API, especially to Windows developers. When you're working on Microsoft platforms, you'll sometimes work with the .NET crypto APIs. So this extra class exposes some additional APIs modeled after, well, as you can probably guess, the .NET crypto APIs. Now, NetFX Crypto does not attempt to cover the full scope of crypto available on the .NET framework. It only includes features that aren't present in the WinRT style APIs, or more specifically, not present in Pcl Crypto's WinRT Crypto class. When using Pcl Crypto, or really any crypto strategy, it's very important to understand which algorithms you have at your disposal. So let's look at symmetric encryption as an example. Pcl Crypto has support for several algorithms and common variations. And at first glance, it appears that Pcl Crypto provides a very large selection, as you can see here on the slide. See, we have the symmetric algorithm enumeration with many, many variations and options. However, not all algorithms are available on every platform. And this is because they're not present natively or not included in the mono runtime. Again, Pcl Crypto does not implement any of its own cryptography. So it's not going to attempt to fill in those missing features. And if you attempt to use an unsupported algorithm on a given platform, it will throw an exception. So when developing cross-platform solutions, of course, you want to select an algorithm that's available on all of your supported platforms. And you can select algorithms that are supported in the mono runtime, or consult the Pcl Crypto documentation and source code to verify support. Now this might sound confusing, but I have some good news for you. Generally, if you choose current standard algorithms like RSA and AES, you should have no problems with cross-platform compatibility. iOS in particular tends to not support older, less secure algorithms. So again, stick with the current standards and it should be smooth sailing. So in this section, we had a great introduction to Pcl Crypto, and hopefully now you see that it is a very strong choice for cross-platform cryptography solutions. In the next sections, we'll be using Pcl Crypto to perform various cryptographic operations. And our first section, we're going to look at using cryptographic hashes. And specifically, we'll try out hashing locally stored passwords. So, we're going to explore how to generate a cryptographic hash, and then we'll see how to apply it to passwords. We'll then use our password hash to validate subsequent login attempts. Now, you may want to protect data stored locally with user credentials like a username-password combination, and you may be protecting personal data in your application, or protecting cache data from a web service. Apps are becoming more powerful as they interact with the physical world, so things like home automation, for example, it could actually be very, very costly or dangerous to have unregulated control of your application, and you may really consider adding an additional layer of protection beyond just the simple protection available by default on the platform. By that I mean things like making the user enter a PIN before accessing the operating system. It's preferable not to store passwords directly on a mobile device. So let me ask you a question. Do you trust the security on your mobile device absolutely? Can you be sure that the file system cannot be read? Or maybe another question, as a developer, can you be sure that the file system of your users' devices cannot be read? What if you lose your device? What if a compromised application is installed? Or what if a user jailbreaks their device? I think you get the idea. Generally, it's accepted mobile devices are just not considered all that secure. And from a security point of view, we consider anything saved to the device to be potentially accessible to an attacker. So I think I've convinced you this is why we do not want to store passwords directly. Users often use the same password on multiple accounts, so a leaked password may do more harm than just exposing the data stored in your application. Instead, we prefer to store a cryptographic hash of the password. The hash can be considered unique to the user's password, and it's highly difficult to determine the original plain text password from a hash, such that we do not consider it possible to retrieve the password from the hash when using a sufficiently strong hashing algorithm, something like SHA-256. So we can store the hash to the device and use it later for validation, and even if that hash is exposed, it's not damaging the user. So what is a cryptographic hash? Well, the hash is a result of a one-way mathematical operation that runs on your source data. Your source data is the input, and it will generate a very nearly unique value for every input. But it has a couple of very important properties. One, the hash should not leak any information about the source data. So what that means is by examining the hash on its own, you should have no idea what source data was used to generate that hash. As well, applying the hash algorithm on the same input will result in the same output. So the hash operation can be repeated and compared. We're not going to discuss the mathematics involved, But I can tell you that it's extremely computationally expensive to try and determine the source, i.e. your plain text, from the resultant hash, such that it's considered, by practical means, impossible to reverse. And we often think of a hash as a digital fingerprint. Now, when hashing a password, it's best practice to add random data to the password before hashing. And we call this random data the salt. We use a salt to make dictionary attacks and hash table attacks impractical. So using a salt makes attempting to reverse the hash significantly more computationally expensive. And this offers better protection against weak passwords. So as you can imagine, if someone enters a 4-character password, an attacker could try all combinations of 4 letters and probably redetermine the hash value, and then they'll know what your source password was. So by adding that random data to your password, it means they have to do a lot more operations, significantly more operations, to brute force attack the hash. It also means that by using a larger salt, that it's no longer reasonable for an attacker to generate a hash table. And this would be a table that has really a set of input values and hash results. Again, by having a much larger source data, a much larger password with the salt, the size of that table is far too large to store. Now, the salt does not need to be kept secret. So by adding a salt, it just really makes the brute force attacking much harder. So a salt should always be generated from cryptographically random data for each value to be hashed. And fortunately for us, Pcl Crypto does expose random data generation. And it does this via the generate random method. And you can see that here on the slide. And it's common practice to use a salt that is the same length as the hash output. So for example, when using a 256-bit hash, we would use a 32-byte salt, regardless of the length of the password. Now, to make a password hash usable, we need to be able to compare the results on future login attempts when the user re-enters a password. So we need to be able to recreate the hash given the same password input. So this means we need to, of course, save the original hash when the user, for example, creates an account. But we also need to save the salt used so we can recreate that hash and validate a login attempt later on. Now, like our encryption algorithms, Pcl Crypto gives access to a selection of cryptographic hash algorithms, and not all of them are available on every platform. Now, you should consult the Pcl Crypto documentation and source code to verify a specific algorithm. Now, the SHA-2 or SHA-2 algorithms are available on every platform. So this includes SHA-256, SHA-384, and SHA-512. And currently, the industry considers SHA-256 or better to be a very reasonable choice for hashing. If you're protecting highly privileged information, it would be wise to consult with a security expert and talk about what level of security should be used. But for our casual purposes, we're generally happy with SHA-2 algorithms. So, how do we do it? Well, Pcl Crypto uses a factory pattern to create something called a hash provider. So as developers, we'll choose our algorithm, as an example, SHA-256. Now recall that Pcl Crypto may use either the platform-specific crypto APIs or the APIs supplied by the runtime, and the exact implementation you get may vary by platform. Now, the creation of the object that implements the algorithm is hidden behind a factory method. And the provider is the thing that implements the hash algorithm that you want to use. Now, the factory pattern allows us to code against a consistent API for all platforms. Let's take a look at some code. So to hash a password, we first concatenate the password, and this will be in the form of a byte array, with our salt, also in the form of a byte array. Now, the algorithm is loaded, as you can see here, using WinRT Crypto hash algorithm provider open algorithm. We make our selection using the hash algorithm enumeration which presents all the algorithms present in Pcl Crypto. Now, once we have a reference to the algorithm object, we call the hash data method, passing our concatenated password salt combination into the constructor. And the hash data method will return the hash again as a byte array. Now, when working with a plain text password, we need to first convert the password string to a byte array. And this can be done using the static encoding class. Now, the encoding scheme makes very little difference as long as it's consistently applied, and the labs are using UTF-8. Now, to validate a password, we repeat the steps on the previous slide with the new password. Again, making sure to use the exact same salt data that was originally used. We can then compare the original hash with the new hash, and we'll compare those as byte arrays. And of course, if you don't use the same salt, the resultant hashes will not match, and you'll have no way to validate the original password. Now, something that's often mentioned with hashing, and this is important for public-facing systems, is to make the comparison algorithm take the exact same amount of time regardless of the input. And we do this so a potential attacker gains no information on failed password attempts. Now, the specific details about this type of attack are beyond the scope of this course, but you may find it very interesting reading to research on your own, and is something that a security expert will likely discuss. So now that we know how to hash passwords, let's improve the diary application. And we're going to carry on from the existing project. And our very first step is to get the Pcl Crypto NuGet package added to our platform-specific projects. I've already done it for the Android project. I'll add it to iOS now. Packages, right-click, add package, and just search for Pcl Crypto. And it's my first result here, nice and simple. And we've added the package. Now, over in the shared code, I've got another helper class in the security folder. It's just called Crypto Utilities, and it's a number of methods that we're going to use. Notice it's a static class with static methods. It's just some helper methods for our various cryptographic operations. And we'll start with our get hash method. And notice currently it doesn't do anything. It accepts a byte array and a salt for, a byte array of data and a byte array for the salt. And currently it's returned the data. It's not doing any work at all. Now, we're going to use the WinRT Crypto hash algorithm provider to generate our hash. But the first thing I want to do is combine the data and the salt together into one variable. So I'm going to make a new byte array. And we'll call this salted data. And we'll make this byte array the length of our data plus the length of our salt. Of course, we're just going to bind the two together. We're just going to really just concatenate. There's a number of ways of doing this. I'm going to use array.copy. And our source array is our salt first. And then our destination, of course, is our salted data. And the length is, well, this is the length of salt. We're going to copy the whole thing. So our salt is at the start, and then let's add in our data. So again, our source is our data. Our destination is our salted data. Now our destination index is now, of course, after the salt. We want it to go to start copying at salt.length, and the amount is, of course, data.length. And again, this is just a little bit of plain old C# using array copy. Nice and simple. We've got a byte array now that combines our salt and our data. Now, let's get our hash. This is fortunately fairly straightforward. We use the WinRT Crypto class, and it has a property called hash algorithm provider. That's our factory. And we're going to call it its open algorithm method. And that just takes the hash algorithm enum and let's use SHA-256. That should be sufficiently strong. And this returns an iHash algorithm provider. So let's just save that off. Let's call it var SHA. Now, SHA now has a hash data method that takes a byte array. And again, of course, we're going to use our salted data. We're going to hash both the salt and the data together. This method returns another byte array. That's, of course, the hash, and we'll just return that directly. Our next step is to use this code over in our account manager class. But I want to show you one other thing in this crypto utilities class first. If you scroll up, there's a couple of static methods here that are already defined. We're going to leave this top one for now, but the second one, get 256-bit salt, we're going to use in just a moment. And this is going to return our salt. And again, we're just going to use a property on the WinRT crypto class called Cryptographic Buffer, and it has a method called generate_random. This method generates cryptographically random data. We just give it a byte length, and it'll return a random collection, a random byte array. In this case, we're asking for 32 bytes. And so again, this is really just a simple, it's almost a wrapper method. It doesn't really do much, but it just simplifies and just means that we don't have to specify the byte size. So we'll use this get 256-bit salt method in just a moment. So over to our account manager, we're going to do a couple of things. We're going to save the salt, and then later on, we're going to hash the password and save that hash. But let's deal with the salt first. So, create and save account. Notice we're validating our inputs here, our username and our password. Then we're loading the account store, and then we're trying to load an account based off the username. So now, if we don't have an existing account, we're going to make a new account. And that new account is going to store the salt. We need to have the salt saved, so when we validate the password later, once we do the hashing, we have that salt. We'll need the exact same salt to validate the password. We can compare the hashes. So, nice and simple, let's generate the salt. And we saw how to do that in our crypto utilities static class has get 256-bit salt. And that's our byte array. Nice and simple. And we're going to store this in our account object. And that goes in the properties property dictionary. We use the add method. Again, we need a key. Unless we have a salt key const string up top, we'll make use of that. Now, the value to be saved must be in the format of a string. There are no other overloads. There's only one properties dictionary, and it only accepts strings. But our salt is a byte array. So we're just going to Base64 encode this. So I'm going to call convert to Base64 string. That accepts a byte array. That will be our salt. And this returns a string, and that string will be saved now in our properties dictionary. So now let's use the salt and hash our password. So we're all set. We can call our crypto utilities get hash method. And that will return, of course, the hash of whatever data we send in. So we'll get our hashed password back out. That's crypto utilities get hash. Now it takes data and a salt. Now we've got our password, but our password is in the form of a string. We need to pass in a byte array. Now you might be tempted to say, hey, let's use Base64, but that's actually not correct. We just need to convert the string to a byte array, but the string is not Base64 encoded, so we can't Base64 decode it. What we can do though is just use a very simple byte encoding method. And over in crypto utilities, we have such a thing. We're just using encoding UTF-8 get bytes. So you see we have a string to byte array method, and then we have the reciprocal byte array to string. And again, just for convenience and just to make sure that these two methods match up when we're converting and converting back, that we're using the exact same encoding scheme. It doesn't really matter which encoding scheme we use as long as we're consistent. So this is perfect. So this we'll call string to byte array. We can pass in any arbitrary string and it will give us a byte array. So our first property is the data. Crypto utilities string to byte array. Our string, of course, is the password. That's our data. And the salt, of course, we have, and that one does not need to be converted. It already is a byte array. And that's it. The hash is actually fairly simple to generate. And we're just going to update now our account properties to store the hash password instead of the plain text password. So let's edit this here. I'll do it side by side for comparison. So properties, add. We'll use the same key because we're not going to use the previous password. We're not going to save the password string anymore, so we'll just reuse that key. Now again, like the salt, our hash password is in a byte array that needs to be saved as a string. And again, convert to base64 string is the right way to do this. Convert to base64 string. We'll give it our hashed password. And we're all set. Now, something very important here though. We are modifying this code. So if you've already created an account, that account is stored on your device, maybe on your simulator. And so if you now try to validate that account, well, we're updating our code to use a hash password instead of the plain text password. So you're going to need to reset your simulator or create a new account to actually validate. The old account with the old password is not going to work. And speaking of validation, this is our last step. When we do the validation, we log into the account, and now instead of just comparing the password strings, we're going to compare hashes. And that means we need to retrieve the salt, hash the new password, and see if those hashes match. We'll do all this in our login to account method. So again, we'll get our account store reference, and we'll get our account. And we'll change our logic here just slightly. We're no longer going to compare the password directly in the dictionary. So let's just see if our account is null. And if it is, we'll return false. We definitely need to retrieve that account. And now we need to do some work. I'm going to make a couple of temporary variables here. They'll both be byte arrays. So our salt, we're going to retrieve that from the account object, and the hashed password. So the salt, I'm going to pull this out of the account, out of the dictionary. Now I'm going to be a little bit direct here. I'm not doing a whole lot of validation. Again, we know what we're storing and what we're loading, so this is fairly safe. In a production app, I might code a little bit more defensively, but this is perfect for this demonstration here. So maybe I'll step back. So we know this salt is stored in the account, in the properties dictionary, and it's stored under salt key because we put it there. Now, of course, we need the byte array, and we know that we've stored this as a string, so we need to really base64 decode, if you will. So I'm going to use the convert from base64 string. This accepts a string, and we'll return our byte array, and this is going to return our salt to its former form. And so now we've got our original salt, and we've got our new password. It's now time to hash the new password. And this really is actually very similar code to what we did above. We could actually even do a little bit of copy paste here if we liked. It's the exact same code. We're going to call crypto utilities get hash. We'll do a string to byte array on the password. Again, the password has to go to a byte array, but this time this is the new password. We're attempting to log in, and we're using the same salt. And we'll do a little bit of inline validation here, and you might break this out a little bit more in a production application. And we're simply going to check the stored hash and see if it matches our new hash password. Now again, remember the stored hash has actually been base64 encoded, and it's actually stored as a string. So we can do a really simple string comparison here and just convert the new hash to a string right away. And then we can simply do a direct comparison of the strings. Otherwise, we have to do a slightly more complicated byte array comparison. Either way is perfectly fine in this case. There, we're all set. We've now stored our password hash, and now we're rehashing and comparing the hashes, and now we're never saving the password directly. And you might be thinking, well, what's the big deal? Does it really matter? Well, for this particular application, although we're not using it yet, we're going to use the password to protect our diary entries. And so if in the unlikely event the password does leak, you are protecting this user's personal data. But also keep in mind that most users use the same login credentials for multiple places or multiple accounts. So leaking the password for your diary app might actually be a substantially more important security breach. You may be leaking passwords they use for other accounts as well, and a malicious hacker might use that to exploit, say, social networks. So always a good idea. So let's run the application and try it out. Again, remember that we can't use the same account and password that we did in the previous attempt that has been stored as plain text, and you could easily add a little bit of code to check that and even update existing accounts if needed. I'll make a new username. I'm going to type in Zam. I'll create a new account, and then we're in. I'll stop the application and run it again, and we should be able to log in with the same account. I'm going to use Zam. Let's put in an invalid password, try to log in. The login has failed. You can see we've successfully reused the salt, hashed a new password, and validated it. Now that we have a secure way to validate a password, let's use this technique along with symmetric encryption to secure data locally on the device. Now in this section, we'll start by creating an appropriate key, and then we're going to use that key for both encryption and decryption using Pcl Crypto. As we discussed earlier, from a security point of view, we think of any data stored on devices to be potentially visible to an attacker. So if we're going to store personal or sensitive data, we should definitely provide some protection. As an example, we may be storing health data or even personal pictures, or more likely even cache data from a protected web service. Now, Xamarin Auth is not suited for this case, and it's really not designed for it. Xamarin Auth stores strings, so you would need to convert binary data to and from strings, which can increase its size, i.e. when using Base64, but more importantly, Xamarin Auth is not designed to store very large objects. It's meant to store short strings. So we'll use symmetric key cryptography to secure these larger objects. Now, symmetric key cryptography uses a single key for both encryption and decryption. And most symmetric algorithms are relatively fast, so they can be used on larger amounts of data like our images or even databases, and provide reasonable performance on mobile devices. Now, as we discussed, Pcl Crypto exposes a number of algorithms for its various cryptographic functions, and this of course includes symmetric encryption. The algorithm selection is done via the symmetric algorithm enumeration, and along with the other algorithms we've discussed, if you're using Pcl Crypto across multiple platforms, you need to verify the algorithm is implemented by consulting the documentation or the source code. Performance isn't usually a big factor when using symmetric encryption on modern mobile devices, so you'll most likely be choosing the most secure algorithm available. The Advanced Encryption Standard, or AES, provides a good balance of performance and security, and it's considered a reasonable choice. However, again, this is general advice, and if you are protecting more sensitive information, you'll likely want to have a conversation with a security expert to decide on the proper algorithm to use and the implementation. So let's take a look. We create the key for symmetric encryption from key material. Now the key material is provided to Pcl Crypto as a byte array, and the byte array can be randomly generated or derived from a user entered password. Now, to avoid brute force and dictionary attacks, we'll use randomly generated data in our next exercise. And for AES, we have 3 key lengths corresponding to the 3 different options of security in AES, and the key length must match the algorithm. Pcl Crypto uses a factory provider pattern to create cryptographic keys, and this is similar to what we saw earlier when talking about hash algorithms, but it does require an additional step. Let's take a look. So as developers, we'll select an algorithm, and we'll also provide the key material. Often, this is cryptographically random data, of course with an appropriate key length based on the algorithm. And we use the provider factory to generate an encryption provider. Now this provider knows the algorithm, and the provider creates an I cryptographic key object for you. And the I cryptographic key encapsulates both the key material and the algorithm. And this object is what you'll use for your encrypt and decrypt operations. And to use symmetric encryption, we must first generate a provider. This is done using WinRT Crypto Symmetric Key Algorithm Provider Open Algorithm. We pass in a symmetric algorithm enumeration to select the algorithm, and we then create the key using the create symmetric key method, passing in the key material. Now in this example, we're using the generate random method to create a 32-byte array of random data to be used as that key material. Unlike hashing, when encrypting data, we do not want the same source data, i.e. the same plain text, to generate the same encrypted result, which we call the ciphertext. So to ensure each operation creates a unique result, we use something called an initialization vector, often shortened to IV. And this is common practice when using the AES cipher block chaining algorithm. And a full discussion on initialization vectors is beyond the scope of this course, but it is good practice. Decryption is very similar to encryption. So we use the WinRT Crypto cryptographic engine static class, and we use its Decrypt method, and we pass in the key, and we must use the exact same key material that was used for encryption, and the ciphertext, i.e. the byte array that was the result of our encryption, and the initialization vector. And the IV must match exactly to the one used for encryption. Now, when securing local data, we need to persist several pieces of data. We need the key material. We need the initialization vector. And both of these can be stored securely using Xamarin Auth's account store. Now, of course, we also need to save the encrypted data, i.e. the ciphertext. And since this is already protected, you can use any storage mechanism that makes sense for your application. Right? It's encrypted data. So this includes saving it to local settings, commonly saved to the file system, or even storing it within a local database. Remember that the key material and the IV are stored as byte arrays, but Xamarin Auth is only able to store string data. So to convert our byte arrays to strings, we'll use Base64 Encoding. And Base64 is a binary to text encoding scheme that represents our binary data in an ASCII string without any loss of data. And Base64 encoded strings can be safely decoded back to the byte arrays when restoring values from Xamarin Auth. I'm now going to add symmetric encryption to the diary application. And we'll use this to encrypt and decrypt the diary entries, as well as completing the functionality. We'll make this app a fully working diary app. The first step is to create a new key, and we're going to use cryptographically random data for that key. Make it really, really difficult to brute force attack. And we've got another helper method over in the crypto utilities class. You may have noticed this earlier, the get AES256 key material method. And you'll notice this is simply calling into our WinRT Crypto class, cryptographic buffer property, and the generate random method. Again, this is going to generate cryptographically random data, and we specify the length in bytes. This will return the perfect amount of random data for our AES-256 key. You may also notice it's the exact same call we use for our salt. And again, these are just helper methods. You don't have to structure it like this, but this just makes sure we've got the byte size just right for our application. So we'll create a new key when we create a new account, and we'll do that in our create and save account method. And so we'll do this after we've added everything else. We're going to create a key and we're going to add it to the properties dictionary. So a new variable key material. And this is easy. Cryptographic utilities get AES-256 key material. And this is going to come back as a byte array. And we'll save it in our account properties, just like we saved the salt. Account properties add. We need a new key. We've already got one defined, KM key. And of course, we need to convert this to a string because our key material is a byte array. So just like our salt, convert to base64 string key material. And you could even simplify this. This could go down to one line. Maybe just grab this and do that. We don't need this temporary variable here. Next, I want to add in the logic to perform the encryption and the decryption. We'll do the encryption first, and we'll do this in our crypto utilities class. You'll notice we have, again, stub methods for encrypt and decrypt. Looking at encrypt, we take a byte array plain text. Remember that plain text is a convention. It doesn't necessarily mean it's text. It's really just any unencrypted data. In our case, we are encrypting text, but it could be images or other things. And it accepts the key material. That, of course, is going to be the basis for our key for the encryption. And the method is going to return an encrypted, a ciphertext byte array. So our first step when using Pcl Crypto is to get the provider. We're again going to use our WinRT Crypto class. It has a property called Symmetric Key Algorithm Provider, which has an open algorithm method. This takes an enumeration, and we're going to use AES cyber block chaining. It's sort of it's a given standard, and it's usually a good choice. Now, we'll use the provider to generate the key. Now, the key is a combination of two things. It knows both the algorithm and the key material. So on the provider, we're going to call create symmetric key, passing in the key material. And of course, this could be condensed down to one line of code, but it gets a little bit long. This is just a tiny bit tidier. So great, we've got a key that we can use to encrypt. But when doing symmetric encryption, we always want to use an initialization vector. So let's make an IV now. We call WinRT Crypto, cryptographic buffer, generate random. And for this, our IV size we've defined as 16 bytes. You'll notice we're using the exact same generate random method that we use for both the key material and the salt. This cryptographically random data turns out to be very, very useful. And of course, we always want to create a new initialization vector every time we encrypt. So now we've got all the pieces, it's just time to perform the encryption. So let's get our cipher. And to perform the encryption, we go back to WinRT Crypto, Cryptographic Engine, and Encrypt. Now notice we're not specifying the algorithm. That's all done by the key. We just call encrypt, we give it the key has the key material and the algorithm. We of course need to give it our plain text, our data, and our initialization vector. An optional parameter, always a good idea to include this. And there we go. Now, we have the cipher, we have our encrypted data, that's fantastic. But we have no way to decrypt this unless we have both the key material, which we've saved off, and the initialization vector. Now we could have some way of pulling that out and saving that with our account object, but typically with symmetric encryption, we actually attach the initialization vector with the cipher. So I'm going to make a new variable called cipher text. Really, again, not always text, just representing our encrypted values. Make a new byte array. This is going to be the length of our cipher plus the length of our initialization vector. We're just going to combine the two into one. And I'm going to show you a slightly different way of doing it this time. I'm going to use copy2. So I'll copy the initialization vector to our new byte array. We'll put that at the start, and then we'll copy our cipher to our new longer ciphertext byte array. And of course, we're going to copy it after the initialization vector, so we'll start at iv.length. And we're all set. And now we'll just simply return our ciphertext, which is our encrypted data with the appended initialization vector. Now, while we're here, we might as well implement the decryption method as well, our Decrypt method. This is going to have some similarities to encrypt. Notice that decrypt takes the ciphertext this time, and again, the key material. And of course, we need the exact same key material. But notice we're not passing in the initialization vector. We're assuming that that is attached to the ciphertext. So just like before, we'll create our provider. I'm just going to copy paste this. No need to type it in twice. We're also going to create our key based on the key material. And again, I'll copy paste. Almost safer. Make sure we're using the exact same values or exact same algorithm. So now I want to copy the initialization vector out. So I'll make a local variable called iv, and you may have wondered why I had a definition for the initialization vector size earlier. So I can do this. So I know the exact size to create for a byte array. I know how long our IV is, so I know how much data to copy out of the ciphertext. And just for fun, I'll use array.copy this time. So our source is the ciphertext. We're going to copy it into our new IV variable, and the length, well, heck, let's do IV. Could be IV size or IV.length. Doesn't really matter too much. Now we also want to get the pure cipher data. Let's make another variable called cipher. It's a new byte array. Now this is going to be the length of the full ciphertext minus the length of the IV. And again, we'll use array.copy and pull it from the ciphertext. We're going to start after the initialization vector. I'm going to copy it into Cipher. And of course, we want it the size of Cipher to get the full data out. So now we've broken apart. We've really done the exact opposite of what we did in the Encrypt method. We simply need to call the Decrypt method. WinRT Crypto, cryptographic engine, Decrypt. Same parameters. Takes the key, takes some data. Of course, this time our data is our cipher, right? Not the ciphertext. The cipher is just the pure encryption data without the initialization vector. The IV goes in separately as the third parameter. This will return a byte array, so we'll simply call return. And I'm gonna open up the code behind for the editor page. Now this is the page, this is the UI where we enter the text for our diary. And at this point, this is where we're going to encrypt it and save it once the user has completed their diary entry. And again, we have some stubbed out methods. You're welcome to look through this code later. You have it in your downloaded package. But you see we've got two methods to fill in. We have got get diary text and get ciphertext. And these are really the two methods that will be called to encrypt and decrypt the diary text. We of course need to encrypt it when the user finishes entering the data, but the user returns to a diary entry and they want to edit an existing entry, we have to decrypt it here as well. And that's what the get diary text method is used for. So we'll start with get ciphertext. Now let's show you where this is called. Simply on the button Save Clicked event handler. So when they click that save button after entering a diary entry, it's going to encrypt the data and store it. So let's do this. I'm going to start right away. I'm just going to make a local variable called key string. Which we'll use in just a moment here. Now this class is given the account object. So when the page is created, the account object is passed in. This is the account for this particular user. So we already have that and we can use it. So let's check the account. And so see if the properties dictionary has the key material. And we're going to pass that out into key string. So we're just going to load our key. And if for some reason that key is not present, we'll just return null. Now really, ideally, this should never happen. Just missing a paren here. Perfect. The key material should always be saved, but we'll just do just a little bit of sanity checking here. So now we need the key material to perform our encryption. So we need it in the form of a byte array. So we're just going to convert it from a Base64 string. Convert from Base64 string, and that's our key string. And finally, we're just going to return. Notice the method returns a byte array, so we're just going to call crypto utilities encrypt. How great is that? One last problem. Our data needs to be in the form of byte array. Well, we know how to solve that. We even have a helper method for that. Crypto utilities string to byte array. That's just going to use the UTF-8 encoding. We'll give it our diary text and our key material byte array, and that will perform our encryption. We have just one more step before we try out our new diary application, and that's to fill in the get diary text. And again, this is just so we can load in previously saved and encrypted diary entries. Remove the existing code. We'll start out just the same. We need that key string. We'll need the key material for both operations. And really, I can copy this code here as well. Let's pull it out. Except in this case, get diary text returns a string, not a byte array. So we'll return string.empty if this fails. And ideally it never will. It'll be just a little bit defensive. Very similar, we now want to convert our key string to its proper byte array key material. And we can almost just copy and paste that last line. It's so similar. But let's do it slowly. I'm going to call crypto utilities decrypt this time. So what's our ciphertext? Well, that's actually passed in here. How perfect is that? This actually comes from a database if you want to dig through the code. We've got our key material here. So here is our plain text in the form of a byte array. We don't really want it as a byte array. We want it as a string. So the result of this, we're going to convert the byte array to a string. And again, we'll use our crypto utilities helper method. And now we have our plain text in the form of a string. And you know what? That's it. That's all we need to do. I'm just going to return from here. And we're all set. So let's run the application. I've reset the simulator so there are no accounts present. So we'll make a new account first. So of course hashing the password and saving it with the account. You can add a diary entry. We'll save that. Our entry appears. We can go back in and edit and save. But more importantly, this data is being encrypted and decrypted. I won't go through the full mechanics of storing data in a database, but I will show you that our getDiaryText and getCipherText methods are being called. So when I load our diary entry, getDiaryText is called. It passes in that saved ciphertext. And then look at the byte array, of course, it's just random bytes at this point. But we are using our crypto utilities, Decrypt Method, and then that data is being pushed in to our editor. When I save, our getCipherText method is called, and that is, of course, from the button save clicked handler. And again, we're using our Decrypt method, and this ultimately then goes and gets saved in our database. And this brings us to the end of Enterprise 170. Thank you again for joining me here today. If you have any questions about any of the material covered today, please remember, as a Xamarin University student, you do have exclusive access to the Xamarin University forums, and you can always schedule one-on-one time with an instructor by scheduling an office hour through the Xamarin University website. Again, my name is Adrian Stevens. Thank you very much, and I hope to see you in a live class very soon.